We will now look at chemistry paper 2. So, like the video I did before on chemistry, I will look at combined science, foundation content, higher content, and then triple content. So let's start with what is common amongst all chemistry areas, whether you're doing foundation combined or foundation or combined higher or triple. You will be tested on relative formula mass, on empirical formula, on moles. So just to save time, you need to revisit these calculations. Group 1 and group 7. Now please bear in mind that for foundation, group 1 is mentioned on the advanced information. For higher, group 1 is not mentioned on the advanced information, and neither is group 1 mentioned on the triple. However, unless it says specifically topics not assessed, I would still be cautious of revising these topics. So the key things to look at. So what I'm going to do is I'm going to compare group 1 and group 7 chemistry. So in group 1 we're looking at lithium, sodium, potassium, and in group 7 we're looking at fluorine, chlorine, bromine, and iodine. In both cases, as we going down the groups, I'll write it here. So on going down the group, these are the common trends. Atomic radius increases. In other words, outer electrons are further from the nucleus. So they experience lower or weaker nuclear attraction. That's common feature. Another thing you could mention is electron shielding increases as you go down the group. What that means, therefore, and what's significant is that the reactivity of group 1 metals as you go down the table, as you go down the group, increases. The reactivity of group 7 decreases as you go down. But the reasoning is exactly same as the reasoning here. So, because the outer electrons get further from the nucleus, they experience less attraction, easier to lose an electron in group 1. So it's easier to lose an electron. And for group 7, it's harder to gain an electron. These features are common between group 1 and group 7, which I would mention here. Other things with group 1, I think which is important to note here now is reactivity of group 1 with sodium reacts with oxygen to form sodium oxide, burns with a yellow flame, balance it. And the other key reaction is sodium plus water. It forms sodium hydroxide and hydrogen. So in this reaction you will see fizzing. In this reaction you will if you use a universal indicator paper, you will see the solution turning purple. Now we must balance all equations. So sodium is a solid, water is a liquid, of course, sodium hydroxide, and gas. Now the reactions become more vigorous as you go down the group. Sodium reacts more vigorously than lithium, and potassium reacts more vigorously than sodium. Potassium catches fire, burns with a purple flame or lilac flame when it's added to water. So, but the general equation is that excuse me, lithium floats on water, fizzes less vigorously than sodium. So that's pretty much group 1. Now, what about group 7? Well, group 7 elements appear as diatomic, i.e. two atoms joined together. They are covalently bonded. They are simple covalent structures. They do have low melting points or boiling points because they have weak intermolecular forces between their molecules. General reactions. Chlorine can react with sodium to form sodium chloride. Chlorine, the test for chlorine gas is it turns damp litmus paper, and please remember this test, red, and then it bleaches it white. That's the test for it. Another important reaction is hydrogen reacts with a halogen to form, and these are solutions that are formed when hydrogen reacts with chlorine. It forms actually a gas, but when you add the solution through water, they dissolve in water to form acidic solutions, so hydrochloric acid, and so on. Now, in terms of redox reactions, halogens very easily become halide ions, i.e. they gain electron. So, and the reason why fluorine gains electron more easily than, say, chlorine is because fluorine is smaller than chlorine, so it can gain electrons much more easily. Okay, those basically are some of the reactions of halogens. The other very important reaction of halogens is displacement. Extremely important reaction, possible 6 marker could come up. A more reactive halogen displaces a less reactive halogen from a solution of its compound, e.g. chlorine, water can react with sodium bromide and it will form bromine and sodium chloride. Now you need to know the colors. So bromine is an orange solution, and therefore that's the color change. The ionic equation, again for higher papers you must know these ionic equations. You can clearly see that bromine chlorine is reduced, so that's reduction, and bromide is oxidized, that's oxidation. So important reactions of halogens. Noble gases is not mentioned on the higher. However, noble gases are inert. They have full outer shell of electrons. They can't gain or lose electrons, and that's the reason why they are unreactive, and that's the main reasoning of those. Okay, next topic is the rates topic. Rates is an extremely important topic. Rate of a reaction is the change in the concentration or the amount of reactant or product produced over time. So rate is basically the change in the concentration or amount of reactant or product over time. In every reaction, if I was to plot a graph of concentration against time, products are formed and reactants get used up. So I would say in most reactions, that's exactly what's happening in those reactions. So that's on that. Now the other thing I would like to mention, and I'll mention it here now, and that is you've got to be able to work out the rate from a graph of this nature. So I'm going to put some numbers on here. Now this is time in seconds. 30, 60, 90, 120. This is concentration. Okay, roughly. So what's the rate at 30 seconds? Place a dot on 30. You need to take a ruler, draw a tangent line on the ruler. Make sure you do this with the ruler. Draw a tangent line on the point, and then you do a gradient of that line by doing what I'm just doing, drawing a triangle, and then it's whatever dy, change in y over x, is your rate. So in this case, very rough, it's about 0.2, because the rate has concentration has gone from 0.2 to about 0.4, and the change in time is about 70. That would be your rate. Units, concentration is in mole per dm cubed, so that would be mole per dm cubed per second. So that's how you would measure, that's how you would work out rate from a graph. Now, how do we measure rate? What experiments can we do? So, measuring rate, and this is a core practical. Investigate the effects of changing conditions of a reaction on the rates of chemical reaction. So, how do we measure rate? One way of measuring rate is you collect gas. Simply, you need a conical flask, a delivery tube, gas syringe. This is a gas syringe. You need a bung. There's your mixture like calcium carbonate and hydrochloric acid, and you measure volume of gas collected every 15 seconds for about 2 minutes. That's one way of measuring rate. Then there is a famous disappearing cross method. Now this is a good method of changing the concentration. Here in both of these two methods I've explained, you could change concentration of the acid, keep the surface area of calcium carbonate the same. Alternatively, you can change the surface area of calcium carbonate and keep HCl the same. Or you can change the temperature. You can warm hydrochloric acid and see the effect of temperature on rate. In the disappearing cross method, we use something called sodium thiosulfate. We place this in a conical flask, a mixture of hydrochloric acid and sodium thiosulfate. We place this on a white tile with a cross. You need a stopwatch. So for all the rate measurements, you need a stopwatch. You place hydrochloric acid, you put sodium thiosulfate, mix the two, start your stopwatch and time how long a yellow precipitate forms. Now in this reaction, what are the factors we can change? We can change the concentration of hydrochloric acid. We can alternatively change the temperature. So we can have hydrochloric acid and sodium thiosulfate in say 5 different water baths, set at 20 degrees, 30 degrees, 40 degrees, and 45 degrees, and possibly 50 degrees. So these are the ones we can look at. Those are the main experiments you are expected to know. Oh, one more is same as this one, i.e. measuring, collecting gas, but instead of using a measuring syringe, you can have a mass balance and you can measure the decrease in mass every 15 seconds. So that's another way you can do that. The next topic is heat changes. Catalysts and activation energy. and the factors that affect rate. So that's next we want to do. Factors affecting rate. Now, in terms of factors affecting rate, rate can be affected by temperature, pressure, or concentration, surface area, and catalyst. Now, you need to apply the collision theory. What the collision theory is about is, for a reaction to occur, particles must collide, and they must collide with sufficient energy, which we call EA, activation energy. So for a reaction to occur, particles need to have, there needs to be frequency of collisions per second per unit of time, and there needs to be collisions that have sufficient energy for reaction to occur. So let's talk about temperature, pressure or concentration, surface area, and a catalyst. A temperature, when you increase temperature, so let's say we increase temperature, what happens? Particles gain kinetic energy, move faster, collide more often. When they collide more often, that increases the frequency of collisions. Frequency of collisions goes up, that means there are more successful collisions per unit time, per minute. So more particles will now collide with energy greater than activation energy. When we increase pressure or concentration, there are more particles per unit volume, meaning in the same space there are more particles. When there are more particles, then there will be more frequent collisions. When particles are together, they will collide more often. There will be more successful collisions will be more frequent. More particles will have energy greater than activation energy. That applies to pressure and concentration. When you increase the surface area, I make something a powder, then there is more surface for collisions to occur. So the frequency of collisions goes up. So more particles will now collide with energy greater than activation energy. A catalyst speeds up a reaction, and it provides an alternative pathway with lower activation energy. And I'll talk about reaction profiles next, because next we're looking at heat changes. Reactions can be exothermic and they can be endothermic. An exothermic reaction means heat is released. Temperature of the surroundings goes up. An endothermic means heat is absorbed, temperature of the surroundings goes down. So a reaction profile for an exothermic reaction means reactants have more energy than products. So the enthalpy, the change in energy is, it's exothermic because heat is released. And if we put reaction profile here, then this is your activation energy. And what a catalyst does is that a catalyst basically provides an alternative pathway with lower activation energy, and that's catalyst. For an endothermic reaction, reactants have lower energy than products, so that's reactants. This time the arrow goes up because heat is absorbed, and this time your reaction profile looks like that, and that is your activation energy. Activation energy is the minimum energy that the reactant need for reaction to occur. What experiment can we do to measure heat changes? We can have a polystyrene cup, because a polystyrene cup is an insulator. You can rest it in a beaker. You place a solution like hydrochloric acid, measure its temperature, then add some sodium chloride hydroxide to it, and then measure its temperature afterwards. So you measure the initial temperature and you measure the final temperature. The temperature changed, the maximum temperature reached. If the temperature goes up, then the reaction is exothermic. If the temperature goes down, then the reaction is endothermic. So good examples of this sort of experiment is hydrochloric acid reacting with sodium hydroxide, or copper sulfate reacting with zinc, which is a metal displacement reaction. Both of these reactions are exothermic. Now, for higher paper, bond energy calculations. Bond energy calculations is where energy change is the energy of bonds broken minus the energy of bonds formed. You will be given data here. You do not need to memorize anything here in order to remember any of these figures. So there's nothing here you need to memorize in terms of numbers. So let's look at a simple reaction between hydrogen and chlorine forming HCl. Your bonds broken here are this one, so that's bonds broken, and bonds formed here is 2HCl. You work out the value of bonds broken, you work out the value of bonds formed, and out comes an answer. Right, next topic is fuels and earth science. So fuel, and this is the last topic for combined and for combined higher and combined foundation. In this topic we're going to look at hydrocarbons, crude oil, natural gas, alkanes, combustion and incomplete combustion and complete combustion. These are some of the main topics. Now that doesn't mean that you don't go through the early atmosphere, you don't go through things like the changing atmosphere and the atmosphere today, because I think you should go over those things and those questions can come up. However, I'm just focusing mainly on the advanced information received here. Right, crude oil. Crude oil, naturally found in the earth. It's dug, it's drilled, North Sea in Britain. We've run out now, but we used to have a lot of crude oil there. Crude oil is a source of hydrocarbons. The fractional distillation of crude oil produces different fractions of hydrocarbons, and when we carry out fractional distillation, different fractions will be collected at different points. So you will get gases at the top of the fractionating column, and then you'll get petrol, kerosene, diesel, fuel oil and bitumen at the bottom. So these basically are what's happening as crude oil is fractionally distilled. The fractionating column is hotter at the bottom, about 350 degrees, and it's about 20 degrees at the top. Gases ignite easily, they are good fuels, and as you go down, as you look at the arrow, then the rate of ignition decreases, viscosity increases, and then the bigger the hydrocarbon, the less useful it is. Hence, we will carry out cracking of hydrocarbons. Now, what is a hydrocarbon? Hydrocarbon is basically a compound that consists of carbon and hydrogen atoms only. Uses of crude oil. Crude oil is used. The products we get from crude oil are good fuels used for energy, for power stations. The feedstock for raw materials for the petrochemical industry, and fuels will burn, and with burning you will need to know what combustion is. So combustion is basically a hydrocarbon reacting with oxygen, forming carbon dioxide and water. Again, you must balance these equations. Now, the hydrocarbons that features for combined science is alkanes. Alkanes have a general formula of CnH2n plus 2, methane, ethane, propane, butane. They are part of the homologous series, which is a series of compounds that have the same general formula. Each successive member differs by CH2, and their physical properties are there's a gradual variation in their physical properties, i.e. boiling points increase as the size of the molecule increases. However, they have the same or similar chemical properties. Incomplete combustion means lack of oxygen, and it produces carbon monoxide, which is a poisonous killer gas. It basically replaces oxygen in the body, in the bloodstream, and that lack of oxygen could lead to brain hemorrhage in that respect. Okay, so basically that's the problem with carbon monoxide. Other problems with burning fuels is they release sulfur dioxide. Sulfur is naturally found in crude oil. Sulfur dioxide is a acidic poisonous gas, causes acid rain, and also when fuel is burnt in cars we produce oxides of nitrogen, because nitrogen reacts with oxygen in the car engine at a temperature of about 1000 degrees to produce nitrogen monoxide. Nitrogen monoxide is also a pollutant. It can cause photochemical smog. It can lead to acidic rain. So the next part I've already mentioned is cracking. Cracking is a process of breaking large hydrocarbons into small, more useful hydrocarbons like C10H22, C7H16 and C3H6. C7H16 can be used as for petrol. C3H6 can be used to make plastics. So we're producing more useful products. And the other things I think that's important is alternative fuels for cars instead of, say, petrol. So there's hydrogen, there's also electric cars, which is becoming a big thing nowadays. So those are the alternatives you can explore. That now really completes combined science. So the video now will continue for triple science, and I will go over things which are essential for triple science now. So if you are not doing triple science, you can log off now, or you can switch off now. So for triple science, you do need to know the history of the atmosphere. Okay, so key concepts: group 7, rate of reactions, heat changes in chemical reactions, that's already discussed. Fuels and earth science, that's already discussed. What we need to look at now is the history of the atmosphere, because that's mentioned. Here, I would divide the history of the Earth into three broad eras. 4.5 billion years ago, let's say 2 billion years ago, and let's say 2 million years ago to present. So how has the atmosphere changed? 4.5 billion years ago, the atmosphere had carbon dioxide, water vapor, methane, ammonia, because volcanoes were erupting. 2 billion years ago, the atmosphere temperature dropped, water vapor condensed, dropped to the ground, formed oceans. Oceans formed, and with the formation of oceans, plankton started to evolve. Simple plants, they started to photosynthesize. That reduced carbon dioxide and released oxygen. So that's one. This is all a theory. Another theory is that about 2 billion years ago, rocks containing bands of iron oxide started to form. The oxidation of iron suggests that the levels of oxygen were increasing. And then there's also fossil evidence of microorganisms that may have produced oxygens. So that's the basic, that's a very basic, very brief summary of the history of the atmosphere. Oceans also trapped carbon dioxide because it's soluble in water, in rocks, in fossils, forming things like calcium carbonate. Is there a link between rise in the Earth's atmospheric temperature and carbon dioxide? Well, here you've got to give an argument. It's not a question of yes or no, but an argument. Now, what are your greenhouse gases? Please note the greenhouse gases are methane, water vapor, and carbon dioxide. There are no other greenhouse gases. What happens is the energy from the sun is transferred to the Earth by infrared or light. Some energy is absorbed by the Earth's surface, which warms it up. The warm Earth emits infrared, and some gases like greenhouse gases, they absorb infrared radiation. When these gases re-emit this energy, some of it goes back to the Earth's surface. In other words, these gases emit some of the radiation back onto the surface of the Earth, and the Earth's temperature, or the surface temperature of the Earth, increases, and that is known as the greenhouse effect. So simply, these gases absorb infrared radiation, and they don't emit all of it back into space. They re-emit some of it onto the surface of the Earth. The link of greenhouse gases leads to droughts, leads to variable temperature changes, weather changes, adverse weather effects around the world. Some areas will face droughts, some areas will face flooding, and that will destroy habitats, it will destroy plants, and so on. So that's some of the problems and effects of climate change. Again, please have a read of this yourself. Now the next topic, now again, alkanes and alkenes, the test for alkenes, the production of ethanol, what are alcohols, carboxylic acids, addition polymerization, condensation polymerization, esters, uses of polymers. None of this is mentioned in advanced information. However, I think some of these areas will be tested. So I would not discard any of these. So the topic I want to focus on now is a qualitative analysis and test for ions. Flame test. Make sure you know how to do a flame test. You need a nichrome wire. You need to clean it in hydrochloric acid. You need to place that in the solution under test or a solid under test. This flame test is for metal ions, lithium ion, sodium ion, calcium ion, copper ion. When you place these in blue Bunsen flame, lithium ion produces a red flame color. Sodium produces a yellow-orange flame color. Calcium produces orange-red flame color. Copper produces a blue-green flame color. And potassium gives you lilac flame color. Learn these, and you also need to know what flame photometry is. What about tests for positive ions? This is what I call PPT, precipitation test. Aluminium ion, so here we add sodium hydroxide to a solution of aluminium ions, and this will produce, and I'm writing the ionic equation here, a white precipitate of aluminium hydroxide which dissolves in excess sodium hydroxide. Ion 2 will produce a green precipitate of Fe2 plus 2 hydroxide ions forms FeOH2 solid. Copper 2 will produce a blue precipitate of copper, and the other one you need to know is iron 3 will produce a brown rust type precipitate of iron 3, and calcium 2 will produce a white precipitate which does not dissolve in excess sodium hydroxide, and that's how you can differentiate between aluminium and calcium ions. Again, you must learn these ionic equations. Now, the other test you need to know is ammonium ion. Ammonium ion is you take a solution of ammonium chloride or solid ammonium chloride, add some sodium hydroxide to it in a test tube. This will give off ammonia gas, and you will test ammonia gas with red litmus paper. You will use damp red litmus paper at the mouth of the test tube, and that will turn blue. Ammonia is an alkaline gas. How do you test for carbonate ions? You add dilute hydrochloric acid. It will fizz because it produces carbon dioxide. You can pass carbon dioxide through lime water, which will turn cloudy. How do we test for sulfate ions? You add a solution of barium ions, barium chloride. You get a white precipitate of barium sulfate. I am giving you ionic equations because I am quite sure that you will get asked about these. So let's say magnesium sulfate can react with barium chloride. You will get a white precipitate of barium sulfate, and magnesium chloride will be a colorless solution. Next, halide tests. You need acidified silver nitrate. Chloride ions will give you a white precipitate of silver chloride. Bromide ions will give you a cream precipitate of silver bromide, and iodide ions will give you a yellow precipitate of silver iodide. That's nicely summarized for you there. The next bit, and that's the last bit, is on bulk and surface properties of matter, including nanoparticles and Just checking my textbook actually, just to see what else I can talk about this. Nanoparticles are extremely small particles. They are to the power of 10 to the minus 9. So nanoparticles basically, so let's look at nanoparticles first. 10 to the minus 9 meter. Extremely small particles. These do occur naturally. They have been applied, the applications have been involved in modern techniques as well. Their large surface area to volume ratio makes them good catalysts, thus nanoparticles. So they are also used in sun cream because they absorb harmful ultraviolet radiation, which can cause skin cancer. So they're used in sun creams. They are good catalysts. They are stain resistant in that sense. Risks of nanoparticles, none known yet. At the moment, we don't know. Some suggestions are that they can be toxic, but we don't know much about that yet. You could get a question on, let's say a cubed shaped nanoparticle. So you've got a cubed shaped nanoparticle which has size of 20 nanometers. Calculates its surface area. So its surface area will be 6 number of sides times 20 times 20, which comes to 2400 nanometers squared. What about its volume? Well, volume will be 20 times 20 times 20, which is 8000 nanometers squared. And then what is the surface area to volume ratio? Well, that's simply 2400 over 8000. So that's surface area to volume ratio, and that comes to 0.3. Other things, just very quickly to mention then is other properties other things you could be tested on will be what's a composite material, reinforcement and matrix, and what are laminates. You can have a read of things like that, and uses of polymers, metals, glass, and clay ceramics. That's a very quick review, and all the best, and I wish you the best for the exam.